From its vantage on the 10,000-foot summit of Maui's Haleakala, the Pan-STARRS project is tasked to find asteroids that might threaten our planet. Its cameras image a full seventh of the sky every night, sifting the firmament for hints of anything that moves or changes. On October 19, the project's computers detected a fast-moving object on images taken the previous evening. An alert went out, and other telescopes picked up the chase. Within a few days, it was clear that an asteroid-like visitor from interstellar space had infiltrated our solar system, and we were witnessing the first-ever flyby of a body from another stellar system. A paper published November 20 in Nature by Karen Meach, University of Hawaii, and 17 collaborators reviews and adds to the growing collection of observations that have accumulated during the remarkable encounter. The object, now officially named 1I2017U1 and also known by the Hawaiian Oumuamua, or messenger from the distant past, is unambiguously extrasolar in origin and exhilaratingly bizarre in nature. Coming from the direction of the solar apex, the point in the sky toward which the solar system is moving as it orbits the galaxy, it streaked toward the Sun with an initial speed of 26 km per second, accelerating to 88 km per second at the moment of its September 9 close approach, well inside of Mercury's orbit. When finally caught by Pan-STARRS cameras, it had already swung past the Sun and crossed Earth's orbit in the outbound direction. The Sun's waning gravitational influence on it is now steering it toward an exit point from our solar system in the direction of the constellation Pegasus. As reported in the Nature article, Meach and her team enlisted a fleet of the world's largest telescopes, including Gemini South, the VLT, and Keck, to monitor Oumuamua's brightness and its spectrum over the course of several nights during the last week of October. The spectral observations point to a very red color, roughly consistent with the hue of comets and other outer solar system bodies. The inference is that, like comets, Oumuamua's surface is covered with carbon-rich material and is likely not very good at reflecting light. The light curves are nothing short of startling. They strongly suggest that Oumuamua is a crazily elongated shard that rotates every 7 hours and 20 minutes. This rate of spin would cause a weakly gravitating rubble pile to fly apart. Oumuamua must be a solid monolith, held together like a rock by its physical strength. If one assumes that it reflects the same fraction of the light that hits it as that reflected by Earth's moon, it is quite similar in both size and shape to the largest aircraft supercarriers. For more than a century, astronomers have speculated about the potential arrival of an interstellar comet in our solar system. It was thus a surprise that Oumuamua showed no sign whatsoever of a coma. At its closest point to the Sun, it was soaking up 20 kilowatts of energy per square meter, and at the location where the Sun was directly overhead, its outermost skin was heating up fast. Yet effectively nothing was geysering up and out, suggesting the arrival of an asteroid rather than a comet. The mere fact of Oumuamua's discovery suggests that a staggeringly large number of similar objects must be drifting through the void. Several factors, including the direction and the distance of the close approach, permitted Pan-STARRS to make the discovery. Most similar-sized interstellar objects that come as close to the Sun as Oumuamua will elude Pan-STARRS surveillance. After taking the various observational biases into account, Meach and collaborators calculate that there is always about one Oumuamua-like object passing within the sphere defined by Earth's orbit, a value that is in fair agreement with estimates published during the past 2 weeks by other groups. Given its trajectory, it's extremely unlikely that Oumuamua was recently ejected from the planetary system of a nearby star. Almost certainly, it has been traveling through our Milky Way galaxy for hundreds of millions if not billions of years, and so if we assume that its passage was not a fluke, we can calculate that the galaxy contains a quadrillion trillion such objects, 1027, enough to account for 2 Earth masses of material for every star in the galaxy. This vast sea of interstellar shards has some profound implications, as the ejection of debris from a newly forming planetary system is no easy task. Lofting an object like Oumuamua free of its parent star requires the gravitational assistance of a planet that both has a substantial mass and is located at a fairly large radial distance. In our solar system, all 4 giant planets and especially Jupiter and Neptune are capable of slinging small bodies into interstellar space. The terrestrial planets, however, fall well short, as do the vast majority of the known extrasolar planets. If Oumuamua-like objects abound, and if they're composed of icy outer system material, then nearly every star in the galaxy must host a Neptune-like planet at a Neptune-like distance. On the other hand, in the highly unlikely event Oumuamua is indeed a refractory slab of rock or metal, as suggested by its complete lack of coma, then its appearance is extremely hard to understand. Only a few % of stars host planets that are capable of ejecting volatile free debris from warm regions deep within a gravitational well. They flat out can't generate the vast overall swarm implied by Oumuamua's recent passage, suggesting that another visit by a similar object won't happen for a very long time. As it departs into the depths of the galaxy, Oumuamua can expect to fly for roughly 10 quadrillion years before it visits another star with such proximity. At that far distant time, the galaxy will be a very different place, in which all the stars that now shine warmly down on planets will be expired white dwarfs, warmed a few degrees above absolute zero by the flicker of proton decay. References: Jewett et al., 2017, Interstellar Interloper 1I2017U1 Observations from the NOT and WIYN telescopes http://sarxiv.org 1711.05687.pdf Lachlan, G. Battigan, K. 2017 On the Consequences of the Detection of an Interstellar Asteroid http://sarxiv.org abs 1711.02260